Yeah.
Yeah.
I'm gonna check right now. Bro, I think I'm in the 80s or 70s.
I was going for 100.
What did you get?
I got 72.56. Because the Indian doesn't what you said? Yeah.
I don't know. Wait. It's loading.
All right, folks, what do you think? I think the volume in the room dropped a little bit, so let's start from the top. What can you do anytime you have the same terms on top and bottom of a fraction? And I'll give one here. Let's say I have x plus 2, x minus 7, and then x minus 4, and x plus 2. So, Erica, what can you do anytime you have a same term on top and bottom? Yeah, you get to cancel it out. Now, that's a fun word, cancel it, isn't it? Cancel it. Got a problem in your life? Cancel it. Got an annoying friend? Cancel it. Got a term on top and bottom? Cancel it. Why are we really canceling it? Are we really canceling it? What's really happening there? I mean, I guess we are canceling it. We're simplifying it. It equals 1, right? And so if you have a term that equals 1, it doesn't change the value of the expression, so there's no point in having it there. It would be kind of like if I wrote down the number 8, and then I wrote down the number 1 next to it. Like, why would you bother keeping the 1 there? It doesn't help anything. It kind of makes it look more confusing. You're like, is that an 18? What's that dot doing there? And so you wouldn't bother overcomplicating the expression. You would just get rid of it. And that's what we're doing when you have the same term on top and bottom. It's technically equal to 1. When is x plus 2 over x plus 2 not equal to what? Here's a really fun question. When is x plus 2 over x plus 2 not equal to 1? No, with or without parentheses. You've got the same thing on top and bottom. I'm hoping this question blows your mind because, I mean, we're all in pretty much strong agreement that if you have the same thing on top and bottom, it's equal to 1. I mean, we kind of specifically said that yesterday, that you can rewrite 1 as 2 over 2 and 3 over 3 and, you know, y over y and happy face over happy face. And so when is x plus 2 over x plus 2 not equal to 1? Yeah, when x is negative 2. What happens if x is negative 2? Is 0 over 0 equal to 1? That's actually not. 0 over 0 is not equal to 1. Remember yesterday when we made this big old long chain of fractions, we never said 0 over 0 is equal to 1. And that might sound like a very subtle, philosophical, like kick in the face, like, well, come on. I mean, everything over itself is equal to 1, but not 0. And you could play with that by typing it into your calculator. You can type anything into your calculator you like. 13 divided by 13, 107 divided by 107. Everything's going to give you 1 until you type in 0 divided by 0. Try it. You know, convince yourself that there's just the exception to the rule. You cannot divide 0 by 0 to equal 1. That is what? What is it technically? 0 divided by 0 is 0. It's not 0. It's undefined. Again, type it into your calculator. I encourage all of you to type it into your calculator to see that 0 over 0, first of all, it's not equal to 0. It's not equal to 1. And in fact, it's not equal to anything. It's undefined. Well, that's kind of helpful. That tells us a little bit about what it means later on when we see the same thing on top and bottom. Even though we casually get rid of it and we cancel it out, well, I'm skipping ahead to one of my last questions. We'll come back to it. Next, When considering a rational expression, what's the first part you should look at? So here I have, again, another rational expression, x plus 2, x minus 8, all over, let's say, x minus 9 and x plus 2. What's the first part of this rational expression that we should look at? The what, peasant? What's kind of like the most important part of a fraction that we need to look at when it has variables?
Denominator.
The denominator. We need to look at that denominator first. It's of primary importance. Why is the denominator so important?
That's what gives us our answer for x.
It is what gives us our answer for the location of wholes and asymptotes. The denominator is so important because of what it can't be. What can the denominator not be? 0. So the first thing we need to look at when we consider all these rational expressions in chapter 7, first thing we need to look at is just the denominator, because you can't divide by 0. So that's the first tip off to us about some important facets or important details about our function. So we always want to look at the denominator first, because that's the big problem, is anytime the denominator is 0, you get something that's undefined. Okay, what can the denominator never be? Sad. No, 0. It can never be 0. I mean, it can be 0. It's just that then the whole expression is undefined. Okay, when the denominator equals 0, what will you see on the graph? Either a whole or an asymptote. You'll have one of the other. So let's just look at that to remind ourselves. Here's my favorite graphing tool, Desmos. And let's just go ahead and make, I'm going to make one that looks like this. X plus 3 divided by x plus 3 times x plus, minus 2. All right. So here's my graph. And there it is, that nice characteristic shape that we were talking about. I still don't really know what it quite looks like. I suppose if I had 2 of those, I would say it looks like a lovely star. I mean, just look at it. Then it would kind of look like a fun star shape, huh? Like the story of Bethlehem, like the star in the sky or something like that, you know, a star on a winter night. But when you just have one of them, it looks like half of the star. Anyway, that's the characteristic shape of a rational function. So looking at my equation here, my denominator has an x plus 3 in it. So when will x plus 3 equal 0? When x is negative 3, because then negative 3 plus 3 is 0. So what happens at negative 3? If I come over here and look, can you see? Ah, there we go. What happened at negative 3? It's undefined. There's a hole there. And on the other hand, here's x plus 2. When will x minus 2 equal 0? I can't highlight it. There we go. When will x minus 2 equal 0?
When x next.
Yeah, when x is positive 2. Because then 2 minus 2 is 0. So then we look over here at 2, and what's over here at 2? An asymptote. So it is curious to notice that one binomial term in the denominator caused a hole, but the other binomial term caused an asymptote. So what's the difference? Why did one of them cause a hole and one of them cause an asymptote? What's that?
The sign.
It could be the sign. Like you could say, well, anytime it's x plus 3, it's a hole, and anytime it's a minus number, it's an asymptote. But that's not really true.
Because it went below 0?
Because I could change that to negative and change that to plus, and then change that to negative. And now my hole and my asymptote have switched places. Now I have a asymptote at negative 2, and now I have a hole at positive 3. So it's not just the sign of those terms. What else? Maybe this isn't big enough for you guys to see in the back.
Whatever binomials exist, isn't it?
It's what, Rob?
Whatever binomials exist after you've cancelled out the other.
Yeah, after you do the canceling. So notice in this expression, the way I have it now, I know I just switched it all, but right now the 3 is a hole and the 2 is an asymptote. The negative 2 is an asymptote. So this one is the asymptote, and this one is the hole. And why? Yeah, whatever binomial term gets canceled, that's the hole. And whatever binomial term doesn't get canceled, that's the asymptote. Now, we might now be able to answer, why is it that if you can cancel something out, it causes a hole? Because let's remember, what is x minus 3 over x minus 3 equal most of the time? Usually, most of the time, this thing is equal to 1. But when is it not going to equal 1?
when it's positive.
Yeah, when x happens to be 3. Because then when x happens to be 3, you have 3 minus 3 over 3 minus 3, which is 0 over 0, which is undefined. So just when x equals 3, just for that blip of a moment, this whole expression will become undefined. And if you look at x equals 3 right here, just for that blip of a moment, just when x equals 3, then you have a hole. But otherwise, can I get it? There you go. So x minus 3 over x minus 3 typically equals 1. For just about any x value in the universe that you plug in, x minus 3 over x minus 3 would equal 1. But when x equals 3, then it's 0 over 0, which is undefined. And that's what causes the hole. All right. So yes, going back to my question, it was, there we go. When the denominator equals 0, what will you see on the graph? Either an asymptote or a hole. Which is which? The hole is the terms that cancel. The asymptote is the term that doesn't cancel. Last question, looking at the rational expression only, how do you know if you see an asymptote or a hole? Oh, well, we just answered that question. So if I didn't show you a graph, I would expect that you could still look right here and say, hey, Mr. G, there's a hole at x equals 3, and there's an asymptote at x equals -2. Because those are the two x values you can plug in to make those equal 0. And yet this one cancels out, so it's a hole, and this one doesn't cancel out, so it's an asymptote. All right. Well, that's some good general knowledge about rational functions. So let's go ahead and take a look at where we are. Today's March 1st. Happy March. I'm sure you're all very sad about the upcoming break from school. Do we really have the whole week off? We don't have to come here at all? How terrible. How terrible. All right, well, we have those 2 days off, so what do we have now? We have 1, 2, 3, and then 4 more days before your test. I don't know why I didn't put the test right there, but the test would have been the next class period, so March 22nd we'll have a test. All right. Did I not tell you one of these jokes? Which one didn't I tell you?
The second one.
Oh, the second one? Ah, one of my favorites. Why? I tell it differently than this. This says, why did the Scarecrow get a promotion? I like to say, why did the Scarecrow get a Nobel Prize? Why did the Scarecrow earn a Nobel Prize? Because he was outstanding in his field.
I remember that.
I like that one. By the way, folks, have you ever watched the scene in The Wizard of Oz when the Scarecrow gets his brain? It's a really good mathematical scene. It's quite hilarious. Maybe one of these days we'll watch that if we can finish class early one day. It's a good one. All right, well, here we go. Folks, we are on part 2, Beyond the Denominator. Did Noel? No, there's Noel. Noel, you're going to need these. And did Siobhan? No? Okay, here you go. Noel, did you see I had a note on the board with your name? That was to remind me to give you the packets.
Oh,
What, Carlos? Yeah, that one.
beyond the
Yeah, so Beyond the Denominator, part 2. We all saw how important the denominator is. And why is the denominator so important again? Why is the denominator so important?
determine that.
Because it determines asymptotes and holes, and because it can't equal 0. Yeah, can the numerator equal 0? Yeah, that's fine. Numerators can equal 0 all day long, because the expression 0 over 5, that's equal to 0. And the expression 0 over -7, that's equal to 0. So numerators can equal 0, that's fine. It just makes the whole expression equal to 0, provided that the denominator is not also equal to 0. The denominator takes charge there, and then it's undefined. But numerators can equal 0, that's fine. So I know that we already essentially filled this in, right? I'm going to move this so I can write on it with you. And let's just recap what we had said. All right. So we're looking at a new rational function here, 2x minus 12 over x plus 4. And there's a picture of it right there. Again, this is a different function than the one we looked at the other day. And I have it right here. So everyone see the function here? It's the classic rational function. Wait. Except what's different about it? Oh, well, no, I guess nothing is different about it. Wait, is something different about it?
It's the same one.
It does look backwards from the way we've normally seen it. Like 1 over x, the classic picture of a rational function, you've got a piece on the upper right and a piece on the lower left. That's typically what you see. You've got part of it on the upper right and part of it on the lower left. It just so happens that this function we're about to look at has the piece in the upper left and then a piece in the lower right. That doesn't matter. You know, it's in one of two configurations. It's either there and there, or it's there and there. They're both rational functions. They're just flipped. So that's the rational function we're looking at. And can we already, did we already go ahead and label all the details? I think we did, right? Where's the vertical asymptote?
-4.
It's at -4, so everyone make sure you have a dotted line there, and that's at -4. Where was the horizontal asymptote?
2.
Yeah, at 2. So label in, or, oh, there's my y-axis, 2. And then what about the x-intercept? Where was the x-intercept of the function?
6.
That's at 6, okay. And then where was the y-intercept of the function? -3. All right. Those are what we would call our critical values of this function. These are what we're interested in. We would like to be able to just look at a function without looking at the graph. Right? That's the challenge. Just look at the function without looking at the graph and be able to say, where's my x-intercept, y-intercept, vertical asymptote, horizontal asymptote? So that's our main skill. How do we do that just from looking at the function? So, what order did I put these in? Y-intercept, and then x-intercept, and then what? Vertical asymptote, and then horizontal asymptote. Right. Asymptote. Okie doke. And so visually, we already know our answers, and we'll just keep that in mind as we move forward so that we can check our work and see that we actually did it right. So here we go. Let's explore all 4 of these and ask the question, how can we figure it out from the function itself? And the function itself is 2x minus 12 over x plus 4. All right. Wow. Oh, my graph no longer matches. I should erase that. Any thoughts on how to find the y-intercept? How can we find the y-intercept just by looking at the function? Plug in what?
The -3.
Well, we have to temporarily forget that we know these numbers.
Oh.
Forget that we know them. And let's just think, I'm looking at a function here. How on earth would I find the y-intercept? Rico, what's your guess? Solve for x? If we solve for x, and we've talked about this a little bit, not a ton, but anytime you solve for x, like x equals 2, what did we just find? The x-intercepts and the value that makes the equation true, right? So Rico, hold on to that comment until we get down to the x-intercept, because then we know how to solve for the x-intercept. But let's keep thinking about the y-intercept for now. How do you find the y-intercept?
-12 divided by 4.
-12 divided by 4? Why do you say that? Yeah, Rob.
Only because I'm assuming that those numbers are the y, would give us the y, because we already have the x to the left. The wild guess. Don't know if I'm right.
Okay. I like Rob's wild guess. That's just fine. It so happens, wait, what was your guess?
-12 divided by 4.
It so happens that Rob's guess is accurate. That will actually tell us the y-intercept. Oh, and you knew that because it produced the number you expected. You knew you were expecting -3. And so you're like, hey, well, if I divide those, I'll get -3. Well, folks, let's start here. Make a little graph right here, just a little teeny one, and put a little dot right there. And let's just say, what characteristic does a y-intercept have? What do you know about a y-intercept? Like right now, let's just go ahead and claim, you know, what that y-intercept is. What could that y-intercept be?
The x equals 0.
Yeah, the x is 0, right? For sure. Because the point is on the y-axis. So your x value of the coordinate must be 0 because you didn't move right or left away from the y-axis. And then what would my y-coordinate be maybe? 2. Right? So what we can tell just by looking at any y-intercept is that the x has to be 0, right? I mean, I really want you to be convinced on that point. That if you're looking at a y-intercept, the thing you know for sure is that the x-coordinate has to be 0. And again, because you haven't moved to the right and you haven't moved to the left, you're right at x equals 0 in order so that you're on the y-axis. And so that's how we find the y-intercept. To find the y-intercept, you simply let x equal 0. That's it. If you would like to know the y-intercept of any function in the whole universe, you just plug in x for 0. And maybe that'd be better language. Plug in x equals 0. Let x equal 0 means the same thing. So let's take our function, and we'll say f of 0 equals 2 times 0 minus 12 over 0 plus 4. And what does that give us? That gives us what we were expecting. So I'm going to move that over here. And sure enough, if you let x equal 0, you get negative 12 over 4, which is negative 3, which is the y-intercept we were expecting. All right, so that's it. That's done for number 1. That's how you find a y-intercept of any function in the universe. You just let x equal 0. All right, so then how do you find the x-intercept? Enrique already said it, and this is what we already talked about in terms of quadratics, in terms of solving for x. And maybe a nice little reminder, if I have the equation x squared plus 7x plus 12 equals 0, and then I factor it, so it's x plus 3 times x plus 4 equals 0, and then I use the zero product rule to say either x plus 3 equals 0 or x plus 4 equals 0, and then I solve both of those to say x is negative 3 and x is negative 4. Remember, that was my bonus question on the test. What does that mean, that x equals negative 3? What does that mean, that x equals negative 4? What does it mean?
It crosses the graph at either of those.
Yeah, it means that those are my x-intercepts. 1, 2, 3, 4. I've got x-intercepts at negative 3 and negative 4. And what else does it mean? What can I do with negative 3 and negative 4? Plug them in. And if I plug them in, that equation will actually be true. If I plug in negative 3 into here, that's 9 minus 21 plus 12, which is 0. And if I plug in negative 4 up here, that's 16 minus 28 plus 12, which is also 0. So if you want to know the x-intercept, you just have to solve for x. So that's the first thing you could say is solve for x. Right? Because anytime you solve for x, that's the x-intercept of your graph. The other way to say it, though, is to, let's approach it the same way. Take a look at your graph again, and let's just say this is my x-intercept. What do we know for sure about an x-intercept?
The y is 0.
The y has to be 0, right? Because let's just make up a coordinate for this one. What could that coordinate be? Mark? Yeah, what is it? Yeah, it could be 3, 0, right? I mean, it could be anything in the x direction, but you know the y value has to be 0 because it's sitting right on the x-axis. It's not up, it's not down, it's right on the x-axis. So what we can do here now is let y equal 0. Or in other words, plug in y equals 0. I'm writing all 3 of these down not to confuse you, but we're developing our understanding of what we're trying to do here. We're trying to find the x-intercept. And to do that, you have to solve for x, but also specifically you have to let y equal 0. So let's try it. Take your function, jot it down, 2x minus 12 over x plus 4, and set it equal to 0. How do we solve for x now? What makes this tricky?
Wouldn't you have to get rid of the denominator, so you multiply both sides by x plus 4?
That is correct. Yeah, what makes solving this particular equation tricky?
The division.
The fact that it's a fraction, right? The fact that you have a numerator and a denominator. Well, let's just keep in mind our standard algebra trick. Not that it's a trick, it's just standard algebra. Let's say that I had the equation x over 5 equals 2. How would I solve for x? You'd multiply the 5 over, right? X is being divided by 5, so I would multiply both sides by 5. And why would I do that?
To get rid of it.
And to cancel it. And right now, what I'd really like to do is get rid of that denominator. So what shall we do?
Times 6.
Yeah, we'll multiply both sides by x plus 4. Now, why is this so wonderful? Like, we just had a double whammy here. First, what happens on the left? They cancel. What happened on the right?
Times.
It's still 0. Isn't that great? It's not like you have to distribute the 0 and figure out what's over there. It's a 0. So what are we left with? We're just left with the numerator. That's what we're left with. And that's actually the bottom line. If you want to solve for the x-intercept of a rational function, all you have to do, and I'm going to make this our final line here, set numerator equal to 0. That's the actual answer. That's the bottom line. If you want to find the x-intercepts of a rational expression, you just set the numerator equal to 0 and solve for x. And whatever you get, that's going to be the x-intercept. So let's do it. We move the 12 over. We get 2x equals 12. We divide the 2 over. And we get x equals 6. Was that the x-intercept we expected?
Yes.
Yeah. Okay, so far so good, folks. We are producing the values we expected to find by looking at the graph. So let's recap. How do you find the y-intercept? Yeah, you just plug in x equals 0. Right? That's the bottom line. How do you find the y-intercept? You just plug in 0 for x and see what you get. How do you find the x-intercept? You set the numerator equal to 0 and then solve for x. So that's what we found so far. We now know how to, for any rational function, find the y-intercept, and the x-intercepts. Okay, so let's keep going. How do you find the vertical asymptotes or the holes? We already know this. How do you find the vertical asymptotes or holes? You don't set the numerator equal to 0. You set the denominator equal to 0. Set denominator equal to 0. And solve. Right? That's the implication. You set the numerator equal to 0 and solve. You set the denominator equal to 0 and solve. Because what we're really saying is, hey, when is the denominator going to equal 0? When is that going to happen? Because whenever the denominator equals 0, I'm going to get an asymptote or a hole. So we're going to set the denominator equal to 0 and solve for x. And so our denominator was just x plus 4. So we set the denominator equal to 0, solve for x. And apparently, well, for sure, the denominator is 0 when x equals -4. Check, is that correct? What happens if I plug in -4 right now? What would my denominator be if I plug in -4? 0. What would my numerator be if I plug in -4? 2 times -4 is -8. And -8 minus 12 is -20. And -20 divided by 0 is undefined. Yeah, so definitely there's a hole or an asymptote there. Which? Is it a hole or an asymptote that we're looking at? It is an asymptote. After all, did we cancel the x plus 4? No. You only get a hole if you cancel a binomial. Otherwise, it's an asymptote. So go ahead and label x equals -4 is an asymptote. And does that agree with where we said the asymptote was?
Yeah.
Yeah. Folks, this is really exciting. This whole process of what we're doing right here, we're learning the anatomy of a rational function. We should get biology credit for this class, right? Because we're looking at the anatomy of a function. Is that fair to say? Or is that weird to hear me say that? The anatomy of a function. It's like we're figuring out the muscles and the cells and all the bits and pieces. Okay, maybe I'm crazy. Let's do the last one, the horizontal asymptote. Have we said anything about a horizontal asymptote? We've said nothing at all about a horizontal asymptote. And in order to understand a horizontal asymptote, what we need to do is look at a graph and understand what we even mean. So here's the graph. And what do we mean a horizontal asymptote? A vertical asymptote goes up and down, right? It goes up to infinity and down to infinity. Where does a horizontal asymptote go? It goes left and right. And where does it go? All the way to negative infinity. And where does it go? All the way to positive infinity. So what does that mean exactly? Everybody watch. Well. So there's my graph. I'm going to start moving to the right. And what is my graph doing?
Going to positive infinity.
Yeah, it's just heading off to positive infinity, right? What x value am I currently at? 500? And what happens if I keep going? Now what x value am I at? Yeah. Is my graph changing at all?
No.
No, it's leveled off, right? It's leveled off. Now what's my x value? 900? Now if I just keep going, what are we going to see?
The same thing.
Yeah, we're just going to see the same thing forever. Talk about a monotonous life, right? You're just going to keep going to the right and to the right. Can you imagine that eventually we're going to get to 1 million?
Yeah.
Yeah.
And will anything have changed? Nope. We're still looking at a graph that's leveled off. So will we eventually get to 1 billion? Will we eventually get to 1 trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion, decillion?
Sure.
Yeah. Yeah, and the point is that as I plug in, if I plug in a really big number, what is my graph essentially going to equal? What's my output there? Can you see the y coordinate? Right now it says 1.99. Where's the actual horizontal asymptote? 2. And so right now I'm at 1.99. And if I keep on moving to the right, eventually, well, not even eventually, but my graph is getting closer and closer to 2. Right now it's at 1.991. And I'd have to keep going and going, and now it's at 1.992. And no matter how far I go to the right, I'm going to get closer and closer and closer to 2. Well, here's my upshot.
They'll never reach.
Yeah, you never will reach, right? You'll never actually reach 2. But the point is, you can plug in larger and larger and larger numbers, and the overall value should approach 2. So let's look at what that means. All right. A horizontal asymptote, it means, what does it mean? As you plug in larger and larger values of x, what? Oh, did someone say on average? Did you say that?
Well, I said
You'll never quite reach it. But this fraction approaches 1 value, right? So as you plug in larger and larger and larger values of x, this whole fraction approaches a single value, in this case 2. So as you plug in larger and larger values of x, the fraction, or technically rational expression, approaches a single value. That's just what we mean about a horizontal asymptote, is that you're just looking really far to the right, or you're looking really far to the left. And you've either plugged in a really big x value, like 1 billion, or you've plugged in a really big negative x value, like -1 billion. And whether you plug in 1 billion or -1 billion, you're essentially getting the same answer. So everybody, if you want to write it down, you can, but just go ahead and look. I'm going to take 2 something minus 12 over something plus 4. And what I'm going to put in there is 1 billion. Right? Is 1 billion a fairly large number?
Yes.
I mean, it's a fairly large number, I think. So what's 2 billion minus 12 versus 1 billion plus 4? Let's look at that. So 2 billion minus 12, that's 1,999,999,988 all over 1 billion and 4. Oops. There. Well, let's all round, shall we? What does 1,999,999,998 round to?
2 billion.
2 billion, right? I mean, it really just rounds to 2 billion. Does my minus 12 really do much to the value of 2 billion?
No.
Yeah, like if you owe someone $2 billion in debt and then you're like, here's $12, they're like, thanks for nothing. You still owe me $2 billion, right? The 12 wouldn't even mean anything. So you still have 2 billion. And what about the bottom? What does that round to? $1 billion and $4 rounds to $1 billion, right? You still basically have $1 billion. Right? So I guess what I'm showing is that these two terms, the 2 billion and the 1 billion, they really are significant, whereas the minus 12 and the plus 4, they're like nothing. They're like a drop in the bucket. And so what is 2 billion divided by 1 billion? If I were to write it out, what's 2 billion divided by 1 billion? What does that equal? What does it equal? 2 billion divided by 1 billion? What did I do with all those zeros?
Oh, yeah.
What does it equal?
2.
2. What was our horizontal asymptote? 2. Right? So, and would this have changed if I had plugged in negative a billion? What if I plugged in negative a billion? Then I would have essentially had negative 2 billion over negative 1 billion. And what would negative over negative be? What, Pheasant? It would still be 2, right? So here's the upshot, all right? Because in a horizontal asymptote, we're looking really far to the right, big numbers, really far to the left, big numbers. And so essentially all that really matters is this term. In fact, all that really matters is that term right there, right? Because the minus 12 is pretty much nothing, and the plus 4 is pretty much nothing. And all that really matters is the leading terms. So here's what we're going to do, folks. Here's the definition. To find your horizontal asymptote, I'm going to put a star here. Find the ratio of the leading terms. So what are my leading terms? 2x and x. Okay, so by definition, those are my leading terms. You know how I talked about leading negatives? A leading negative is whenever the first term had a negative on it. Well, these are the leading terms. So what is 2x over x?
2.
What happens to the x's?
Cancel.
They cancel and you get
2.
2. And that's the value of the horizontal asymptote. Okay, first of all, we've done it. We have now seen how to find the y-intercept, x-intercept, vertical asymptotes, and horizontal asymptotes of any rational function. So let's recap. To find the y-intercept, what do? You just plug in 0 and see what you get. If you want to find the x-intercept, what do? I'm going to call on some people here. Kylie, if you want to find the x-intercept, what do?
Set the numerator equal to 0.
Yep. And if you want to find the vertical asymptote, what do, April? You set the denominator equal to 0. And if you want to find the horizontal asymptote, what do, Beth?
You find the ratio of the leading terms.
Yep. Okay, so folks, that's it. I'm not saying that at this point you should have all that memorized, but these 4 techniques you do need to memorize, right? Like in the last chapter, you learned all those different factoring techniques, GCF, leading negative, basic, non-basic, factoring by grouping, difference of squares, perfect square binomial. You learned all those things. Well, right now you want to memorize these four techniques that if I gave you a rational function and you're not allowed to look at a graph, you could still numerically calculate the y-intercept, x-intercept, vertical asymptote, and horizontal asymptote. And that's it for that. So again, that might feel a little overwhelming, but we're going to practice it. You know, that's what we have these next couple weeks for, is practicing. I just wanted you all to know right up front what we were talking about and what the big picture is. The big picture is that we're looking at rational functions and how they behave and what their characteristics are. Oscar?
So you know these 4 things, that's it?
No. There's like a billion other things you need to know. But these 4 things are critical. They're critical. They're the foundation of this chapter. Yeah. All right. So, folks, let's go ahead and turn our attention over to our notes packet, our Chapter 7 notes packet. Now, I would keep that little sheet that you just wrote. Keep it, because that's going to be a really good reference so you can look back and remind yourself how to find the x-intercept, y-intercept, vertical asymptote, horizontal asymptote. You know, you can take that sheet and put it under your pillow, put it up in your kitchen, hang it above the toilet, somewhere you're going to look at it. So, folks, here we go. I'm going to go back to the screen now. So chapter 7 is all about rational functions. And we've just finished a really nice overview of the big picture. So now we'll go through our notes packet and get into all the nitty-gritty details. All right, so define domain. I left you some space right there. Define domain. In shorthand, the definition of domain is all allowable inputs. That's it. Just what inputs are you allowed to plug into the function, and your calculator will actually calculate a value. Those 3 words are really all you need. All allowable inputs. So for instance, you're not allowed to plug something in to a function that will make the denominator equal 0. That would not be part of the domain. The domain is just the allowable inputs, where if you type it into your calculator, you get an actual answer, like 7. If you type a number into your calculator and you end up with your calculator saying error, undefined, that's not part of the domain. So the domain is just the numbers you are allowed to plug in. So the long definition is the domain of a function is all real numbers in the universe except those inputs that would cause you to divide by 0 or square root a negative. That's the long definition. So if you're in cash cab and they say, what's the domain? You could just say all allowable inputs, and I think you'd win the money. But if you're like at a party and you want to impress people, and you walk up, you're like, hey guys, what are you talking about? Domain? You mean all real numbers in the universe except those inputs that would cause you to divide by 0, square root a negative? Yeah, you know what you mean. That's the domain. So let's try a few, folks. Everyone already wrote it down? That's the definition? Okay, number 1, what's the domain? Now, it's kind of funny. When I say what's the domain, what I'm really asking you to do is find the numbers you can't plug into the function. But then when you tell me the domain, you're telling me the numbers you can plug into the function, right? You don't know what you can plug into the function until you first identify what you can't plug into the function. So what can I not plug in for x? 8. That's it. Just 8. You just can't plug in 8. So right now, for number 1, you would say the domain is everything except 8. Now, there's a couple different ways of saying that. And this is what we're going to learn right now, is how to say that. You could just say, it's set notation. That's a set bracket. The domain is all numbers x in the universe such that x just isn't equal to 8. All right, that's set notation. This vertical line right there means such that. Such that. So what we're saying there is the domain is a set of numbers, and it's just a set. It's just, look at all these numbers. And you're saying any number in the universe except x just can't equal 8. That's set notation. The other way you could do it is as a number line. And on a number line, if x can be anything other than 8, what would I shade?
X.
First of all, what kind of circle do I put on 8? An open circle or a closed circle? Open, because open means not included. So this is a little bit of a review of number lines. You put an open circle on 8 because you're not including 8, but then what numbers are you allowed? Everything to the right and everything to the left. And what we're saying in that number line is we're basically saying any shaded number you see, which is all the way to infinity and all the way to the negative infinity, any shaded number you see, except for 8, you can go ahead and plug into that function and it will equal something. So please, someone choose a number over here. Nathan? Choose any number over here.
16.
Okay, 16. I can go ahead and compute 4 over 16 minus 8, which is 4 over 8, which is 1/2. So indeed, I got a value. Someone choose a value over here. Sino?
-4.
-4. If I plug in -4, I'll have 4 over -4 minus 8, which is 4 over -12, which is -1/3. Right? So I can choose any number over here and any number over here, and my function will have a value. And that's what we're saying the domain is. The domain is all allowable inputs that will allow you to actually compute something. Whereas if I plug in 8, that'll give me 4 over 0, which is undefined. Therefore, 8 is not in the domain. Okay, a number line is one way you can show the domain. But typically, to show the domain, we use interval notation. So make a note here. This is called interval notation. Interval notation essentially is a shorthand for a number line. So take a look at my number line. I basically have 2 shaded regions, right? I have a shaded region over here to the left from negative infinity to 8. And then I take a break. And then I have a shaded region over here to the right, which is from 8 to infinity. And the way we write this in interval notation is with parentheses from negative infinity to 8, and then a U, which stands for union, which means or, from 8 to infinity. We're basically saying you can choose any value you like from those intervals. Now these are intervals. What do they look like? Normally when we use a parenthesis and two numbers, we're talking about a what?
Coordinate plane?
Yeah, normally you think you're talking about a coordinate, but this is different. This is a different type of notation. We use the parentheses basically as a shorthand instead of writing a number line. Mathematicians didn't want to keep drawing number lines, and plus it's hard to type a number line to a friend via email. Right? How do you send a number line via email? Whereas it's very easy to use parentheses and just type this out. So this is merely a representation of a number line. I hope that that's clear from looking at right on top of each other. Okay, so how about number 2? How would we write out number 2? We'll do the same 3 methods. So in number 2, what can't you let x equal? Negative 6. Now, of course, you could just do that in your head. You could say, well, I don't want that to equal 0, and it will equal 0 if I plug in negative 6. But if you wanted to be legit about it, you would say, well, I don't want x plus 6 to equal 0. Or maybe you could say, when is x plus 6 equal 0? And then you solve for x and you say, oh, when x is negative 6. So the legit way is you take the denominator and set it equal to 0, and then solve for x. It just so happens that these are so easy you can just do it in your head. You can just look at that and say, oh, negative 6. But really what we'll do is we'll take the the denominator, set it equal to 0, and then solve. Okay, so what's our domain? In set notation, the domain is curly bracket, all numbers x in the universe such that x just can't equal negative 6. That's one way of writing the domain. Or we could draw a number line, and we could say, well, I'm going to shade in every number in the whole universe except for negative 6. And that also is a representation of the domain. Now, how would I write that in interval notation? Remember, interval notation is just a shorthand representation of this number line that I just drew. So who'd like to try it? What do I write down? Elda? Yeah, parenthesis, negative infinity
6.
to negative 6.
Parentheses U, and then negative 6, and then positive.
Yep, that's it. That's interval notation. So, folks, that's 3 different ways you could tell someone the domain of a function.
You want those 3 ways on the test?
On the test, I think I'll tell you one way in particular. And it'll probably be interval notation. Now, of course, if you were just out with friends and somebody said, what's the domain of that function? You could just say, x can't equal negative 6. Now, you could just say it, right? You're amongst friends. You could be like, x just can't equal negative 6. That's the domain. And that would be true, right? It's any number in the universe except for negative 6 that you can plug into that function. Okay, how about number 3? How about number 3? What can't x equal?
There's no x.
Yeah, is number 3 even a rational function?
No.
Remember, we had a requirement for something to be a rational function. What had to be true?
There has to be a variable.
There has to be a variable in the denominator. This is not even a rational function. This is really just a linear function. If you split that fraction up, that's x over 5 minus 6 over 5. This is just the linear function y equals mx plus b. And in fact, that's 1.2. So that's just a line. That's not a rational function. And does a line have an asymptote? Does a line have a hole? No. No, so x can be anything. So in this case, the domain is all real numbers. You can plug anything you want into that function and you'll be able to calculate a value. Your calculator will never say error, undefined.
What's the sign for all real numbers? Isn't it just a capital R with a line down the middle?
Yeah, you could say the domain is R. That R, that kind of capital R with a double line right there, stands for all real numbers. That is a shorthand, yeah. Okay, so now we get to an exciting one. F of x equals x squared minus 36 over x squared plus 3x minus 54. Hey, now we get to really practice our factoring techniques. So in number 4, we have x squared minus 36 over x squared plus 3x minus 54. So remember, in this chapter, we assume that you feel good about just factoring. All right, you just dive right in, you start factoring. So back to the top. What is x squared minus 36? Who'd like to tackle this one? Isis? What's x squared minus 36? As a factoring technique, what factoring technique are we using? What do you want? Yeah, difference of squares. Is that what you said? I can barely hear you. Yeah, difference of squares. And so what will that be, folks? X squared minus 36 becomes?
X plus 6.
Yeah, x plus 6, x minus 6. Now, how about the bottom? X squared plus 3x minus 54. What factoring technique are we using? Just the basic factoring. You know, x squared has a 1 on it. So you just say, what multiplies to make 54? That adds to make 3.
9 and 6.
Yeah, it'll be 9 and 6. Which is which?
Negative 6, positive 9.
Yeah, it'll be, yeah, x plus 9 and x minus 6. Now, folks, we can just assume throughout this whole chapter that they're going to give us problems that will result in us being able to do what? Cancel. Right? They're probably going to give us problems that once you factor it, you're going to be able to cancel something. I'm just saying that's like a good 95% probability. Anytime they give you a problem with trinomials or quadratics in the top and bottom, they want you to factor it and then cross one of them out. So let's immediately label. What does the x minus 6 represent? A whole. And what does the x plus 9 represent? An asymptote. So that's good to just immediately label that, right? We want to keep that in our mind. From now on, for the rest of chapter 7, if you factor a rational expression and you start canceling things out, you might as well go ahead and say, oh, well, that one's a whole because it got canceled out, and that one's an asymptote because it didn't get canceled out. Okay, well, we did a nice job here. We factored it. We now have our final answer, which is just x plus 6 over x plus 9. And now we know that there's an asymptote at negative 9 and there's a whole at positive 6. But the question was, what's the domain? So to do the domain, you have to look at the original expression. So what numbers are we not allowed to let x equal?
Negative 9 and positive 6.
Yeah, negative 9 and positive 6. Even though the 6 is canceled out and you're left with this as a simplified expression, you do the domain on the original expression. So you can't let x equal negative 9 and you can't let x equal 6. So the domain is all numbers in the universe such that x just can't equal negative 9 or 6. That's the set notation. Now, what would that number line look like? Ooh, exciting. Here, I'm going to move up so everybody in the back can see. What does that number line look like? What two numbers will I put on my number line? Yeah, negative 9 and 6. And what will I put on them? An open circle. And then I shade everywhere to the left to negative infinity. I shade everywhere in between. And I shade everywhere to the right to positive infinity. Folks, I do encourage you to actually write negative infinity and positive infinity. I realize that's like a given, right? It's obvious. If you're moving off to the left indefinitely, it goes to negative infinity. But write it down anyway, because that's the number that's going to go in your interval notation. So notice now the intervals are from negative infinity to negative 9, from negative 9 to 6, and from 6 to positive infinity. So we'd write down 3 separate intervals with a u connecting them. So what is our interval? Our interval notation, the domain is from negative infinity to negative 9, or the u means union, which means or, from negative 9 to 6, or from 6 to infinity. That's the domain. This is the primary way we'll be writing the domain. Now I can kind of imagine already that you might be thinking, Mr. G, why on earth would we write it like that? It would be so much easier to just say all numbers in the universe except x can't equal -9 or 6. Right? Isn't that so much shorter? It is so much shorter, and I agree. But there are applications later on where we use interval notation. So I just want you to be flexible and learn both methods so that you're familiar with both of them. All right. Everybody go ahead and try number 5 on your own. And I'll just walk around. Number 5. You'll need to factor the top and bottom, label it as a whole or an asymptote, and then find out what numbers you can't plug in, and then write it down in both a number line, set notation, and a number line. I'm sorry, and interval notation. By all means, work with a neighbor if you like. All right, shall we check?
Yeah.
Let's factor the numerator first. Jennifer, how did you factor the numerator?
For the numerator, I put x plus 4 and then x, oh, plus 2, sorry, and then x minus 2.
Yeah, very good. So that's difference of squares, x plus 2, x minus 2. And how did you factor the denominator? Beth?
X minus 4, x plus 6.
X minus 4, x plus 6?
Yeah.
All right, well, we didn't get to cross anything out. It's not going to happen every single time. It's just something that we want to look for. So what does that tell? First of all, did everyone get that same factoring? Okay. What does that tell us? What does x minus 4 represent? An asymptote. If you just want to write A, you can just write A. I realize asymptote is a ridiculously long word, and it's hard to abbreviate. You could write ass. You could write asim. You could write asim. But maybe we could just say A for asymptote. And so what's x plus 6 represent? Another asymptote. Whoa, that's exciting. Have we seen a double asymptoted function yet? I don't think we have. What does a double asymptoted function look like? I guess we can already imagine. Oh, well, that's a good guess. That there's a part that will look like a parabola? Maybe. So x squared minus 4 divided by x squared plus 2x minus 24. All right, well, there we go. Do you see the double asymptotes? Where's one of the asymptotes? We should already know. Where's one of the asymptotes? At x equals 4 or negative 6. So here's one at x equals 4, and then here's one at negative 6. Are those the two asymptotes? You can see them there in purple and black. So there's our double asymptoted function. I'm going to use that on somebody. Wait, why aren't you just a double asymptoted function? That sounds pretty good. All right, so yeah, who predicted a parabola? Or something that looked like a parabola? Or did I just hear things? Anyway, do you see the part that looks like a parabola? This part down here looks like an upside down parabola, doesn't it? Except it's not technically a parabola because a parabola goes on forever, whereas that thing goes up and asymptotes itself up to infinity. Well, actually, it's pointing down, but yeah. So there's our double asymptoted function. Are there any holes in this function? There's no holes. Nope, because we didn't cancel anything out. All right, so then we're ready to just write down the domain. On the one hand, how would you write that in curly brackets? You'd say the domain is all real numbers x such that x just can't equal what, Sarah? X can't equal
4 over -6.
yeah, 4 or -6. And as a number line, we would have our -4, our 6, our open circles, our negative infinity to positive infinity, and you would shade everywhere else. But then what would our interval notation be? Oscar, what would my interval notation be?
Can you write it out?
Yeah.
So it'd be like the parentheses are
Yep.
negative infinity, comma 4, negative 4,
Yep.
u,
Yep.
parentheses 4, or negative 4, comma 6,
Yep.
u, parentheses 6, and the infinity sign.
And that's it.
You did it,
Why the -4?
yeah.
Isn't it? Oh, it's not a -4. Oh, I did that too fast, and I made everything wrong. Everything wrong. It's okay. It should have been 4 and -6, right?
Yeah.
Okay. You know, I would say, folks, if I'm ever on a roll up here and I'm doing it all wrong, just throw something at me to get my attention. But I said that once to my high school students. The next day, a high school student threw a pencil at me and hit me in the face. I was shocked. I was like, forget it. Don't throw anything at me. This is dangerous. Okay. I'm sorry. I made a huge mistake. Negative infinity to -6, or -6 to 4, or 4 to infinity. Okay. Is that better?
Would it be the circles on sheet in? Is that a hole?
The circles, we don't shade them in because we're not saying that -6 is part of our domain. You can't actually plug -6 into this function. If you did plug -6 into this function, you would get -4 times -8 all over -10 times 0, and you would end up with 32 over 0, which is undefined. So -6 is definitely not part of our domain, and so we're excluding it from the domain. We're saying everywhere else. Yeah. All right. I think let's move on. So number 6, I'm going to leave for you to do for homework. You'll factor the bottom. What are you going to factor out of the bottom? Yeah, the -2. You have a leading negative. You have a GCF. You factor that out, and then you'll have a difference of squares in there. Anyway, I'll leave that to you for homework. So let's keep going. Double asymptoted function. That should be part of it. Okay. So the next part just says simplify the rational expression by factoring. When stating the domain, note which value is an asymptote and which is a hole. I have no idea why I put hole in apostrophes, but not the word asymptote. Anyway, as we do these problems, let's note what are holes. So in number 7, it's just asking us to simplify. So what simplifies? This looks like a problem we did a long time ago, like in chapter 5, doesn't it? So how do we simplify? Yeah, definitely the 3 goes into 39 13 times. And
You would subtract the.
yeah, you can approach the variable part in a lot of different ways, and I realize each of you might have a slightly different approach. You could do the rule where you subtract the exponents, right? So this would become 13, and then for the m variable, you do 5 minus 9, because it's always top minus bottom, so 5 minus 9 is -4. And then for the p variable, 2 minus 1 is 1. So that could be what you do. And I'll remind you better. What is our quotient rule? A to the x over a to the y becomes a to the x minus y, right? That's our formula. It basically states that if you have the same base, top and bottom, you subtract the exponents, top minus bottom. And so that's what I just did here. I had the same base, top and bottom, that's m. So I did 5 minus 9 is -4. And then I had the same base, top and bottom p, so I did 2 minus 1 is 1. Now, how would I simplify that? What does the negative exponent mean in this case?
1/4.
Yeah, I'm going to push the m variable down to the bottom, and I would have 13p over m to the 4th. Did everyone get 13p over m to the 4th? Using whatever method you might have used? Well, what are we saying here? This doesn't look like x and y, and this doesn't look like binomials. What can't m equal? M just can't equal 0, right? But what can't p equal? P could equal 1. Yeah, p also can't equal 0. In the original expression, we can't let our denominator equal 0, so m can't equal 0, and p can't equal 0. I know this problem looks very different from the problems that we've done otherwise, but it's still just a variable expression with variables in the denominator, right? That's a rational expression, anything that has variables in the denominator. And so m can't equal 0 and p can't equal 0 because then otherwise the whole denominator would equal 0. Well, that's it. For this particular problem, that's it. We simplified it, and we went ahead and stated our domain. In this case, we're just stating the domain in terms of what the variable can't equal. All right, well, that's it. Number 8. Y plus 6, y minus 3 over y minus 3, y plus 9. What can we do? Yeah, cancel those y minus 3's. And so the final answer is just y plus 6 over y plus 9. That's the final answer. So our domain would be, the domain, here, let's do set notation. The domain would be all variables y, or all values for y, except y can't equal what?
-9. -9.
Y can't equal,
Oh, positive 3, negative.
yeah, 3 or negative 9.
But I thought y minus 3 was a whole.
Well, that's true, but we're still excluding it from the domain. Domain exclusions are all wholes and all asymptotes. You can't include a whole or an asymptote. So what we're saying here is that the domain is every number in the universe except 3 and negative 9. And which is which? The 3 is what?
No.
A whole, and the 9 is an asymptote. And I might even go ahead and write that right here. The domain is all numbers y in the universe except y can't equal 3 because that would be a whole, and it can't equal negative 9 because that would be an asymptote. This would be a really nice answer right here. You're stating the domain is all numbers y in the universe except y can't equal 3 because it's a whole, and it can't equal negative 9 because it's an asymptote. Junior, thanks for asking that. Basically, what are we excluding from our domain? Wholes and asymptotes. That's it. The domain is everything in the universe except for the location of wholes and asymptotes. So that's really what domain is referring to. Let's see, number 9. I'm going to leave that one for you for homework. Let's try 10. So we have 4x plus 4 over 20x squared plus 28x plus 8. By the way, folks, I just realized my spidey senses went off, and I remembered that my phone went off a long time ago, and I'm just barreling right on past your break. Let's finish this problem, and then we'll take a break. I almost forgot, and you guys, you weren't even going to remind me, were you? Mr. G, come on, let's take a break. You're like, no, let's just keep doing it. Forget breaks. Let's go. I like your attitude. All right, so what do we do here? Yeah, there's a lot of simplifying, isn't it? We have a lot of factoring to do. What's that, Rico? Oh, okay, you're talking to yourself. All right, so what can we factor out of the numerator? Just a 4? And what can we factor out of the denominator? What's the GCF of the bottom? Also 4?
10.
I think also 4. So that gives us 5x squared plus 7x plus 2. Well, that's nice. The 4's cancel out. Now what? We have x plus 1 on top, and then we have 5x squared plus 7x plus 2 on bottom. Can this thing factor? Chances are, right? Because that's the only type of problems they would give us, are problems that you can factor. What factoring technique will we use? We already took out the GCF. There's no leading negative. There's a 5 on the x squared. So we'd have to do the non-basic technique, where we multiply the 5 times the 2, get the factor table for 10. So this is a bit of a problem. You know, you kind of have to like, okay, hit pause on the rational problem. I got to go factor this thing. And so you go find some scratch work. You just find some space on your paper to go ahead and factor that thing. You have to just hit pause on your life and go factor this thing. So 5 times 2 is 10. My factor table is 1 and 10, 2 and 5. And obviously it's 2 and 5 makes 7. So that'll be 5x squared plus 2x plus 5x plus 2. Ooh. Should I write those middle terms backwards?
Yes.
I think so. I mean, it doesn't really matter. But if I put the 5x plus 2 in the other order, then I can obviously take out a 5 from this one and a 2 from this one. And I just like that a little better. So now, factor by grouping, we take out a 5x here. And we take out a 2 over here. And the x plus 1s are the same. And so we get x plus 1 times 5x plus 2. So even though we finished chapter 6, is factoring still part of your life? In a major way. We will keep factoring for the rest of this class. And then even after this class is over, it will haunt you in your nightmares. Factoring will always be part of your life now. All right, so were we surprised to end up with an x plus 1 in the denominator? Why are we not surprised?
Because that's the numerator.
Because that's something that cancels out and gives us a whole. Right? We should be very expectant that they will provide us with something that factors that oftentimes will allow us to cancel one of those terms. So now we cancel out the x plus 1, which is a whole. The 5x plus 2 is an asymptote. And what does that leave us with? What's left in the denominator? What remains in the denominator? I'm sorry, in the numerator. In the numerator? Yeah, I'm not asking for the domain yet. I'm just saying I just canceled out the numerator. What's there? I mean, the bottom is for sure 5x plus 2. What's up top?
1.
I hear a couple different possibilities. Is it 1 or is it 0?
0.
What's the number in front of this?
1.
1. So it's definitely a 1. There's always that invisible 1. Okay, well, great. Well, this is our simplified rational expression. And look how much it's simplified. Boom. That was a huge simplification. You went from something that was nasty, nasty to 1 over 5x plus 2. That's a huge simplification. All right. We now know we have a whole here. We have an asymptote there. So what's our domain? The domain is all numbers x such that x just can't equal what? X can't equal -1 because that's a whole. And then you have to take 5x plus 2 and set it equal to 0. Right? You're using the zero product rule to say, when is 5x plus 2 equal to 0? So again, you might do a little scratch work. You say, when is 5x plus 2 equal to 0? That would be when 5x equals -2 or x equals -2/5. So, and that's an asymptote. That would be our final answer. This is the simplified function, 1 over 5x plus 2, and the domain is the set of all numbers x such that x just can't equal -1 because it's a whole, and it can't equal -2/5 because it's an asymptote.
Would it be positive 2?
I don't think so, because when I moved the 2 over, I got a -2, and divided by the 5, I got -2/5.
Oh, yeah. But on the domain.
Yeah, on the domain, that x is definitely -1 that it can't equal, because that, you're asking yourself, would these numbers, if I plug them in, would it make the denominator equal 0? And if I plug -1 in, that would definitely make this equal 0. And if I plug -2/5 in, that would make this equal 0. Now, folks, I just want to point something out to you before you go on your break. Here. That was one problem, right? I mean, look how good and sophisticated this looks. This would impress your friends and everybody, right? Like, to solve a problem like this, you've got your original rational expression, which you had to factor using multiple techniques. Over here's my scratch work for factoring. and then canceling out the binomials from top and bottom to get our final result, and then identifying the domain of numbers that you can't plug in because that would make the denominator equal 0. This is incredibly sophisticated work. This is incredibly sophisticated work. Now, everybody, let's take a break. It's 9:16. Let's come back at 9:26. Well, Siobhan, no Siobhan. All right, folks, let's keep going. The next two problems, number 11 and 12, just looking at them, what do we have to do first? We have to factor, right? We have to factor the top and the bottom. And that's why I said that going forward, we just assume that you're ready to just factor to keep going with the problem. Now you might say, well, why do we have to factor? Right? I mean, we're factoring, first of all, on the off chance that what?
That there's something to cancel.
That there's something to cancel, right? So that's the first reason we would factor, is because there's a possibility that we could cancel one of those binomials. But what's the other reason we have to factor it? It's not just for the chance that one of them cancels and one of them doesn't, and therefore you have a hole and an asymptote. But why else do we have to factor right now? Do we know what number not to plug in so that the denominator equals 0? We have no idea, right? I have no idea what number to plug in right now that would make this denominator equal 0. So it's for two big reasons that we do have to factor. It's not just some sort of exercise in futility like, oh, okay, let's factor. No, we really do have to factor because A, we have no idea what our domain exclusion is yet. You know, what number can't I plug in for Y? I don't know, but that's the question to ask. what number can't I plug in for y? So we have to factor not just so that we might cancel something and identify a whole, but because we also need to know our domain. So at this point, like for the next couple problems, folks, 11, 12, okay, that's it, 11 and 12. I'll do one with you, you do the other one. The main point is it practices your factoring skills. So the numerator, what multiplies to make 32 that adds to make 4?
-8 and +4.
That'll be 8 and 4. So y plus 8 and y minus 4. So that's the top. And again, I know in chapter 6, I really harped on showing your factor table, showing your work. I think if we could relax that a little bit. Right now, it's just assumed that you're factoring correctly and that you're showing your factor table if you need to. But if you can do it in your head and check it in your head, then that's okay. Like right now, I can check this is true because 8 times -4 is -32, but 8 plus -4 is 4. So I can just confirm that that really is true. How about the denominator? What multiplies to make 72 that adds to make 17?
9.
Yeah, 8 and 9. So I'll go ahead and just put it in, y plus 8, y plus 9. You should always check, is 9 times 8 equal to 72? Yes. Is 9 plus 8 equal to 17? Yes. So you factor at your pace, and then we cancel, and therefore that's a what? Since I canceled it, it's a whole, and the other one's a asymptote. So now our domain is all numbers y such that y just can't equal what? Yeah, y can't equal -8 or -9. For different reasons. It can't equal -8 because that would be a whole. It can't equal -9 because that would be an asymptote. And that would be a full and complete solution. I would give full credit for that. What you're looking at right there, I'd give full credit for that. Even if I don't see a factor table to see how you factored, I would still give full credit for this solution right here. And by the way, how do I know that it's -8? What technical step did I not just show? Yeah, I would have to take y plus 8, set that equal to 0, and say, okay, yeah, y equals -8. And then I would have to take y plus 9, set that equal to 0. So there are certain steps that I'm not showing anymore, like my factor table for factoring and zero product rule, setting this equal to 0 and setting that equal to 0. I think a lot of that we could do in our head. But I still encourage you to show the work if it makes you feel better. Okay, number 12, I'm leaving for you. Let's keep going. Number 13 through 16 is teaching us something special, a gimmick, a trick. Oh, and by the way, I wrote down some steps for you. Would you agree that these are essentially our steps? That you take whatever rational expression they give you and then you factor it. And then you cancel something or not. And then you identify your domain, which again is your domain exclusions. That's really what you're identifying as domain exclusions, which consist of wholes and asymptotes. Right? So that's essentially what we're doing. For every single problem, we'll factor it, cancel something if you can, and then identify the domain exclusions, which are wholes and asymptotes. All right, so number 13, we're about to learn a special new gimmick. And in fact, I think we actually already saw this once. So number 13, we have 2 minus m over m minus 2. Can we cancel those?
No.
No, we cannot. Because 2 minus m and m minus 2 are not the same thing. They look like the same thing. They're really close to being the same thing, but they're not the same thing. So what do we have to do? Yeah, we could multiply one technique. So let's write all of these down. One technique could be that you simply multiply the top and bottom by -1. Why am I allowed to multiply by -1 on top and bottom? What's -1 over -1?
It's a 1.
It's just 1. So I'm allowed to multiply by 1 as much as I like. I can multiply by 1 all day long, and that's not changing the value of an expression. So right now I just multiplied top and bottom by -1, and I want these two expressions to match. So all I'm going to do is distribute the numerator, and that's all. So my -1 times 2 is -2, and my -1 times -m is positive m, and that gives me the -1 over the m minus 2. And now my top, I can switch those two terms, and indeed, now I do have m minus 2 over -1 times m minus 2. Now, what I just showed you is the very formal step-by-step way of doing that. We don't need to keep doing that every single time. I just wanted to prove to you that it really works. That you're allowed to multiply by 1, which I can write as -1 over -1, distribute one of them, rearrange my terms, and sure enough, I just figured out how to make these two expressions the same so that I can cancel them, and what am I left with? Yeah, the top was just a 1 over -1, and 1 over -1 is just -1. So that's actually what that whole expression is equal to. Number 13, that whole expression, 2 minus m over m minus 2, is just equal to -1. This expression is equal to -1 always? When is this expression not equal to -1?
Zero?
When the m is 2. When m is 2, 2 minus 2 is 0, and then 2 minus 2 is 0. 0 divided by 0 is not equal to -1. 0 divided by 0 is undefined. So this expression is equal to -1 for every value of m in the universe except for m equals 2. And that's the point of a domain exclusion, is we're saying, if you were to write it in a sentence, 2 minus m over m minus 2 equals -1, except when m equals 2. Right? That's kind of the upshot of what we're saying about rational expressions, is you can simplify them, but keep in mind, because of a domain exclusion, it's not always equal to -1. It's just equal to -1 when m is any value except for 2. All right. Well, what we would like it now is just a shortcut. So here, I'm just going to show you the shortcut, folks. Anytime at all, you have a binomial, and you want to change the order of the binomial. Okay, this is a definition. This is a shortcut. I see this 2 minus m. I want to switch it into m minus 2. And you can do that by simply putting a -1 in front. All right, so that's the shortcut. You are allowed, anytime you want to, if you want to switch the order of a binomial, that is a subtraction binomial. If you want to change the order of a subtraction binomial, you can do so by just putting a -1 up front. Does that work? Is this numerator the same as this numerator?
No.
It is, but how can we prove it is? Yeah, I can just go ahead and distribute that back in, right? What happens if I distribute the -1 back in? What would I get? And -m plus 2 is really 2 minus m. So the shortcut does work. Anytime at all you want to change the order of a subtraction binomial, you can just go ahead and change it, but put a -1 up front. So here's an example. What if I had 10 minus x, and I want to rewrite that as x minus 10? What would I do? Just put a -1 in front of x minus 10. And that's a legit move. So make a note about it, memorize it. That's something we'll use multiple times. Would it be legal to just switch it? 10 minus x is equal to x minus 10? Is that legal? Is that true? That 10 minus x is the same as x minus 10? Yeah, it's not true. Just think of any value of x. Like, let's choose x equals 5. If I do x equals 5, then 10 minus 5 is 5, but 5 minus 10 is -5, and 5 does not equal -5. So I can't just switch a subtraction binomial. I can only do it if I put the -1 in front. Because now if I plug in 5, 10 minus 5 is 5, and then -1 times 5 minus 10 is -5, and -1 times -5 is +5, and now that really does work. All right? So right up here, that's probably where I'd put that. Simplify each rational expression, remembering to change, just give an example of changing the order. The note I would probably put at the top would be something like note a minus x is equal to -1 times x minus a, or something like that. However you want to write that down in your own words to remind yourself that you can do it. So let's try the next one. The next one is not quite so obvious what we're about to do. 3x minus 27 all over 72 minus 8k. Are those the same binomials on top? I mean, on top and bottom? They're obviously very different. So what do we do first? Yeah, we take out a GCF. So what do we take out of the top? A 3. So that's 3k minus 9. And on the bottom, what can I take out? 8. So that's 8, 9 minus k. Right, so I would like to switch the order of 9 minus k. I am allowed to do that, provided I put a -1 out front. So I will change the bottom to -8 times k minus 9. And that's our technique for switching a subtraction binomial. So now the k minus 9's do cancel, and the answer is just -3/8. Okay, now again, let's think very carefully. We just said that this expression, 3k minus 27 all over 72 minus 8k, is going to equal -3/8. Always? Does it always equal -3/8? It equals -3/8 for every number in the universe except 9. Yeah, what is this thing equal if I plug 9 into it? Nothing. It equals undefined. There's a good guess about the 0. You would have a 0 on top, Beth. 9 minus 9 is 0. But on bottom, you'd have 9 minus 9, and then you'd have 0 divided by 0, and that's undefined. So what we're really saying, folks, is that this whole nasty expression equals -3/8, except when k equals 9. Right? Because k equals 9 would make it undefined. And folks, would it be a whole or an asymptote?
That would be a whole.
It's a whole, because we canceled it out. Anytime you cancel a binomial, it's a whole. I think that one would be worth looking at. Because this is kind of funny. What is that? What does this thing even look like? I've got my 3k, oops. Oh no. I've got, there we go. 3x minus 27 divided by 72 minus 8x. There. What is our graph? What is our graph? What is the graph of? It's just a line, right? And what's the value of the line? Well, it's kind of tough to tell. The y-coordinate is always the same. What's the y-coordinate? -0.375. Type 3/8 into your calculator. What's 3 divided by 8? 3 divided by 8 is 0.375. So look at this graph. The graph is always at -0.375. Except, everybody, do you see 9 right there? What do you think is going to be right there at the 9? A hole. And there it is. There was a hole there because we canceled out the x minus 9 term. You'll notice it equals -3/8 everywhere else. It just doesn't equal -3/8 at 9 because then it's an undefined hole. Okay. Nice, folks. So let's see here. Should we do another one of those? We can do another one. Which one do you want to do, 15 or 16?
16.
Well, I heard both. Which one should we do, folks, 15 or 16? I mean, I guess 15 is so darn quick. Let's just do both. I can't help it. I really wish I could do all of them with you. So y minus 7, y minus 8. What should we do in the denominator? Do I want 8 minus y? Oh, y minus 8, right? So I'm going to go ahead and change the 8 minus y to become negative y minus 8. And then y plus 7, can I just go ahead and change that? Can I just change 7 plus y to y plus 7? Yeah, that's fine. You're allowed to switch addition all day long. You can switch addition. It's just that if you want to switch subtraction, you have to put a negative in front. So now what do we cancel? The y minus 8s? Yeah. So that's my whole. And then the y plus 7? That's my asymptote. And my final answer? Y minus 7 over y plus 7? Yeah.
Okay, so when you put the -1, it's just for that one.
Yeah, it's just for that one binomial. That one single binomial is the only one I switched, so I put a -1 there. Yeah, the y plus 7 I was allowed to switch because it's addition. Okay, so then this was our original. This is simplified, and we would say the domain is all numbers y such that y just can't equal what? 8 or -7. So 8 or -7, and I will label for my audience, that's a hole, that's an asymptote. Keep in mind, now that you know what a hole and an asymptote is, can we pretty much go ahead and sketch this off the top of our head? Even without a graphing calculator, could we already kind of imagine what this looks like? I know that I'll have a hole at 8, so 1, 2, 3, 4, 5, 6, 7, 8, somewhere right up there. I've got a hole there. And then at -7, I have an asymptote, so 1, 2, 3, 4, 5, 6, 7. Here's my asymptote. Here's my graph. How did I do, folks? Does that look like a rational graph?
Yeah.
You know, other than the fact that it's in my childish handwriting, does that look like a rational graph? What else do I need to put? I already have my asymptote. What else do I need to put? A little teeny hole. Bloop. There we go. I just graphed a rational function. It's just a sketch, you know, but theoretically, that's the answer. All right. Let's look at 16. Or should I leave that for you? I think I'll leave 16 for you. I have to leave some problems for you to try. So 16, let's keep going. All right. These problems look like the ones we started with last class at the very beginning. Remember, I gave you a bunch of expressions like this, and what did you do? You just went through and canceled a whole bunch of things, right? That was when we were young in the art of rational functions. We didn't quite know what we were doing yet. We just knew that it was fun to cross things out when it was in the top and the bottom. Now we really know what all this stuff represents. So let's take a look at, say, 17. What all can we cancel? And keep in mind, we still have to factor. The factoring doesn't go away. What can we factor first? What can I factor out of here? Keep in mind, everywhere you see anything, you could wrap parentheses around it.
7.
So here, yeah, I take out a 7, p minus 1, and that's all over p. And in the numerator over here, I have a 2, I have a p, I have another p, and on the bottom here, I have an 8 and a p minus 1. Why did I rewrite 2p squared as 2pp?
Because you can cancel it across.
Yeah, just to make it more clear. I just want to see it better. I have to admit, I love parentheses. You probably all know that about me now. I love parentheses. You cannot write down too many parentheses. In fact, I'm going to start signing cards to my wife as JW. That'd be funny. I'm going to start putting in parentheses just for fun. I'll see if my wife notices. What are you doing? I don't know. All right. So what can we cancel? The p minus 1 and a p, and that's it. So our final answer, oh, and what about the 2? The 2 and the 8?
Oh,
So that's 4. So now what do we have left in the numerator? 7p over 4. And so where were our holes? Because notice we don't have anything left now. Is there an asymptote? There's no binomial left. In fact, there's no variables left. So there's definitely not an asymptote. But there were holes. Where were the holes?
P.
Yeah, when p equals 1 and when p equals just 0. Right? I can't let that equal 0, so p just can't be equal 0. So I would say my domain then is all values p such that p just can't equal 0 or 1. And in this case, the 0 and the 1 are both holes. And there were no asymptotes at all. Okay, well, folks, we're making great progress. We're not where my syllabus says we should be, but we're doing great. It's going to be very simple for us to catch up. We spent a lot of time in the beginning exploring rational functions and understanding them, so we've built a lot of philosophy. We understand what these creatures are. So now we're just going to go through all these technical skills. See, 7.2, we're almost there. And then this as well is going to be pretty quick to go through. So I'm feeling pretty good about where we are. We're just not quite according to the syllabus. What I would do if I were you is now go home tonight and do as much math lab as you can, up to the point where we are now. That's always my recommendation. After class, go home, and do as many My Math Lab problems as you can from what we have already covered. Okay, I stopped a little early so I can pass back your tests. Here are your tests. As always, keep in mind I've given you lots of feedback on the test. So if you got a problem wrong, I didn't just scratch it out. I gave you feedback. I wrote down the formula. I showed you some steps. I sure hope that you're all studying these tests. If you have any questions at all, please come see me in my office so that I can review your test with you. I'm very happy to do so. There goes Sarah.
I have a quick question.
And as always, if you think that I didn't grade your test properly, if you think I was either unfair or I made a mistake, please come and tell me that. I like to think I'm a reasonable person. Folks, in the grade book, just to be clear about confusion, in the grade book, all of the tests are out of 80 points. So if you go onto the grade book, and like let's say you got 100, then you can see an 80 in the grade book. But you didn't get an 80%, you got 80 out of 80. So just to be clear on this test, I wrote both the percentage and the points out of 80. So the test is out of 80, but the percentage I wrote down as well. Okay. Scenery? Is it Tracy? Is it? That's fun. Does anyone else play Tracy? Oh, Tracy Yellow, that's fun. Ron?
I have it right. Oh, but it's plus or minus. It's plus or minus.
Oh, no.
Wait, what number is it? X32. Yeah. Because you have to.
Brandon? Oh, all right. Did everyone get a test? Hey, Michael. And all right, thank you, folks. I think that's it.
Man, I could go on with just a little thing.
Well, I mean, we're in second minute. So what order should it be? Yeah, like number.
We're just like a midterm.
Look at your number line. Number line will go fine. Well, no, it doesn't depend. Number lines go, increasing to the right. But you were thinking.
Yeah, I got that.
Oh, yeah, you want to put the number line in. Like this one isn't. So you got 3, 2, 1, 0, 1, 2, 3, 4. But this number line did want to put in the right. I realize that technically, I know what you mean, but in normal society, people put number lines. Yeah.
A midterm?
No. Is it on the syllabus?